I'm Professor Federico Rossi from the University of Perugia, and my research field is concerning a cool roof, albedo control for global warming mitigation, and building energy requirements and building energy savings, more than renewables, and the application of renewables on building strategies. This works deals with a new model for testing new materials and for testing a new real scenario in order to reduce the urban heat island, and in order to verify whenever new materials or new design could achieve a mitigation on urban heat island phenomenon. Which is the main goal of this work? The main goal, as I told 1 minute ago, is to test new materials as well as coatings, paintings, pavements, in particular to test the surface properties of such materials in terms of urban heat island mitigation effect. The goals deals with also some indication on new design criteria for urban planning. In this way, a better prediction of building energy requirements may be achieved, and for example, also interbuilding effect and microclimatic peculiar condition may be taken into account. Who may exploit these facilities and the result of this paper? They may be exploited by designers, by engineers, by material producers, as well as chemicals and so on, by also lawmakers and politicians, which may be interested on knowing how to plan and how to administrate a urban area better than with the previous tools. So let's take a look to the experimental facilities, and the analogies that we used to use the experimental facilities for representing real scenario. Let's talk about the theoretical model, and let's talk about the baseline analysis, which allowed us to verify the effectiveness, the workability of the experimental facilities too. Then let's also take a look to the next step that will be followed in order to use and to test the experimental and the theoretical model that we have presented here. How all these stuffs work together, that is to say, how the experimental facilities, the theoretical model, and a real scenario, which is constituted by materials, by urban area characteristics and so on, may work together. The real scenario may be tested and may be simulated directly by the experimental facilities through some mechanical analogies. Mechanical analogies allow to reduce the dimension of the measurement device with respect to the real one, in order to measure the behavior to the real one itself. For example, when natural convection is considered, the ratio between the model length and the real scenario one is determined by the ratio by the temperatures that may be achieved in the model itself and that are usually achieved in the real scenario. In this way, we need to control, to drive the difference of temperature on the experimental facilities in order to control also the ratio between L with M and L. The same the same behavior occurs for a forced convection, and in this case the ratio depends on the velocity rather than on the difference of temperatures. Also, the air velocity throughout the walls must be driven by an external force, and in order to control the ratio between L with M and L. We will see in a moment that the real scenario dimension are strongly limited by the experimental facility dimension, and so in order to represent a more wide situation, a theoretical model has been designed which constitute a sort of a link between the real scenario and the experimental facility. In this case, a new material may be proved, may be tested in the experimental facility, may be validated on the theoretical model, and so the effect of this material may be also estimated with a theoretical and experimental combined methodology in the real scenario. Here is the experimental facility, which is located in the roof of a building of our university. As you can see, the experimental facility is composed by two equal arrays, which may be seen better in the next pictures. Here is a closest picture. You can see the two arrays which are composed, each array is composed by a pavement-like surface and by wall-like surfaces. Arrays are exact the same one another in order to reproduce the exact condition in one and in the other. In this way, a comparative measurement may be done between several materials and between different conditions in terms of materials and wall positions. The experimental facility is composed by many frames, and each wall is perfectly insulated by a insulating material in order to reduce the conductive interference between one wall and the other one. Actually, the ratio between the height and the width of each canyon has been determined in 0.5, 1 and 2, which is more or less typical of real conditions. Anyway, this ratio may be adjustable and may be set for any application. The system, the experimental facility, has been equipped with a temperature sensor, with upward-facing pyranometers, and with a weather station in order to control and to measure also the wind velocity and the airborne temperature. The experimental facilities has been also equipped with a lot of thermocouples, that is to say temperature measurement point, which are located in the patterns that we can see in this figure. In this way, we can measure in both the arrays the temperature exactly at the same point, at the same position with respect to sun radiation and with respect to the position of the walls. The number of thermocouples is 48. In this way, we think to have a good representation of temperature distribution all over the two arrays. When the direct representation of real scenario is considered, we need to adopt a mechanical analogy, as I previously anticipated. In this way, as I previously anticipated, the ratio between the real scenario height with the measurement facility height is controlled, is limited by this ratio. For that, the difference of temperature that may be achieved in the experimental facility must be controlled and must be set higher than the natural difference of temperature which may be measured in the real scenario. even for forced convection, these limits limits the ratio between the length of the walls in the experimental facility with respect to the length of the walls in the real scenarios. In this way, for natural convection, we need to use an external wind protection in order to reduce the interference between, to reduce or to neglect the interference between the external wind and the natural convection which would occur inside the canyons. And we also need a warming plate which will be installed in the pavement. The warming plate allows us to get a proper difference of temperature in order to determine the ratio between Lm and L. If we make an example, we can say that if we get a difference of temperature of 55 Celsius degrees, which would describe a real condition of 5 degrees difference of temperature, a scale factor of 0.3 is required. As you can see, this fact is a very strong limit, because if you want to reproduce the behavior of a 10 meters high wall, you need a 3 meters high wall in the experimental facilities, and it is really very hard and tough to be realized. A similar situation occurs when forced convection is considered. In this case, external wind protection shield is also used, but a fan must be used to reproduce a wind velocity in order to control the ratio between Lm and L, which is equal as the ratio between the velocity of the real scenario and the velocity of the air in the model. In this way, for example, making a prediction, if we consider a velocity of 5 meters per second in the real scenario, forcing a velocity of 50 meters per second, a ratio factor of 0.1 is achieved. It means that a wall as long as 10 meters may be represented in the experimental facility by a wall as long as 1 meters. Even such a limit, even if it is a little bit less compulsory than the previous one, reduces a lot the applicability of the experimental facility itself. Anyway, we did a first measurement campaign in order to get a calibration of the two arrays, and this calibration procedure has been achieved from July 24th to July 29th in 2013 in order to assess the thermal equivalence between array 1 and array 2 equipped with the same materials. In this way we can test whenever the two arrays behave in the same way. Data have been registered each 10 minutes, and the result may be summarized in this way. Average difference between homologous sensor is 0.45 Celsius degrees for the entire data set, and 0.05 Celsius degree considering only nighttime data set. The maximum difference from a single thermocouples is 1.1 Celsius degrees. Maximum ground temperature has been measured as 75 Celsius degrees with a relative humidity of 7.5%. Maximum solar radiation has been measured as 1014 watts per square meters. The maximum temperature and maximum solar radiation condition has been the one in which the maximum difference on temperature has been measured in the thermocouples. As we have seen before, the real scenario dimensions are strongly limited by mechanical analysis conditions. And so a theoretical model has been introduced in order to widely extend the experimental facility application cases. In this way, any canyon of the experimental facility, or any way of the real scenario, has been modeled as a cavity in which a radiative balance of energy has been done. In particular, material has been considered to behave in the same way in the visible and in the same way in the infrared. That is to say that, for example, the reflectance of a material has been considered homogeneous in the visible and homogeneous in the infrared, but anyway different in the visible and the infrared. Then a visible energy balance has been written down, and also an infrared energy balance has been also written down. So the two balances have been put together in a global energy balance in which the convection coefficient has been also considered and taken into account. Obviously, the coefficient is different with respect to each of the several surfaces which have been taken into account. Such a coefficient may be used as an analogy coefficient when analogy has been taken into account, and as the real coefficient when the measurement and the theoretical model has been applied to the real scenario, or anyway to the experimental facility. By the usage of the theoretical model together with the real scenario, new material may be tested, and the next step that we are going to do is to test new retroreflecting materials, which may be really very interesting for reducing urban Italian mitigation. In this way, also the theoretical model validation will be possible and will be made applied to a very innovative materials. In order to let you know how a retroreflecting material may be important for struggling and for tackling urban heat island phenomenon, I remind that recently in London a walkie-talkie tower burned a car by reflecting down sunbeams. You may know that reflection, especially in glass surfaces, occurs both for diffusive way and for a Lambert way. When a retroreflecting material is applied, reflection occurs in the same direction of incident light. In this way, sunlight beams may never go down to the streets, but are reflected upwards to the same direction as they come. And probably if a retroreflecting material would have been used in this tower, no burning phenomena would have occurred. Anyway, such new materials for urban Italian mitigation are going to be under test, and the experimental facility and the theoretical model we have proposed today may be useful for that. Thank you for attention.